Hello, everyone. I am David Bernal, and together with Sridhar and Ignacio Grossman, all from Carnegie Mellon University, we are glad to present on the MINLP workshop our work on quantum computing for discrete nonlinear optimization and the Graver Augmented Multiseed algorithm. We all work on this discrete nonlinear optimization problem or mixed-integer nonlinear programming problem, and it has a lot of applications in process systems engineering, which is the area that I work on process synthesis, process planning and scheduling, control, molecular design. But more than that, it has applications in medicine, other branches of engineering, operations research, computational biology, network design. Which problems can be modeled as an MINLP? Short answer, any problem. Using the fact that we can represent any Turing machine, including universal ones, means that every problem can be formulated as an MINLP. And an interesting fact is that addressing this problem in terms of complexity theory is NP hard, and in some cases even undecidable. What I will like to present here is how to address these problems from the perspective of physics. I need to go back to late 1800s with Pierre Curie's observation on the fact that magnets, when they are heated up, they go through a phase transition, which means that they lose their magnetization. So why would nature have sudden change in its behavior? There are several models to predict this. And one of them is actually represented here on the screen. Think of a magnet as a set or a system of discrete particles which can be magnetized either north or south, which we represent with green and red pixels in these pictures. So you can see that since this has more green than red, it's magnetized, and suddenly when temperature starts increasing, some of these green particles start flipping, and at the end, there are as many reds as greens, so in average, this is a non-magnetic material. This particular model was the same that was proposed in 1920 by Lenz, and his student Ising solved the one-dimensional case analytically in 1925. Later in the 1940s, Onsager solved the two-dimensional case analytically, and in the 2000s, it was shown that through an equivalence of the max-cut combinatorial optimization problem, problems with more than 3 dimensions cannot be solved analytically. In terms of physics, this is really interesting given that it gives rise to this notion of universality, where systems with the same number of dimensions and symmetries go through identical phase transitions. And the Ising model is the simplest one in the theory space that can capture such properties. Relevant to what we are interested here, the Ising model can be understood as a subcase of MINLP. In particular, all the nonlinearity is quadratic. There are no constraints, and all the variables are binaries. In the literature, these are known as quadratic unconstrained binary optimization problems, or QUBO, and these are the ones that we are interested in solving. How can we solve them? We can start from the adiabatic hypothesis from Einstein, which means that a system, when it's affected on an adiabatic fashion, it allows every motion. Using this kind of information, we can use the following property of the Schrodinger equation, which is summarized in the quantum adiabatic algorithm. Assume that you have a system, and this system allows for quantum mechanical interactions to happen within. This system can be sitting at a well-defined energy state, which has a ranking among all the possible energy states, and you allow as adiabatic evolution or Schrodinger evolution without measuring it, without noise, at 0 Kelvin, such that that system changes sufficiently slow. Once it reaches a new final state, you open the box, measure it, and this new system is going to be sitting at an energy state which has exactly the same ranking as the one that it started. Well, this can be used in order to devise an algorithm to try to solve interesting problems. How so? The first step would be mapping a problem of interest into the energy function of this quantum system through the Ising model that I showed in the previous slide, and that we cannot easily solve. The second step is that you take a physical system that you can easily control and put it in such a state that it's on its lowest energy state. Later, you can close the box and let it evolve adiabatically such that it reaches the final state that resembles the problem that you're interested in solving. According to this property of Schrodinger's equation, once you open the box and look back into it, it will be on an energy state corresponding to its minimum. Hence, you will be solving your optimization problem. How can we implement this in reality? And there are several ways of doing so. I will show you two through quantum computing. First of all, there are several models of quantum computers right now. One of them are quantum annealers. The quantum annealers are devices that run a single kind of quantum algorithm called quantum annealing. And you can think of this kind of algorithm as a finite temperature implementation of the adiabatic quantum computation that I just told you about, where a system easy to set up is isolated and then transformed into a final system that resembles an optimization problem of interest. This is an analog computation, and the best known example of this are D-wave quantum annealers. The other case are gate-based computers, which are a little bit more popular given that Google and IBM are building devices of this kind. And what they do is that they implement algorithms through quantum operators or gates. And several of those algorithms are designed in order to solve these QUBO problems that we were mentioning. Among them, there exists the quantum approximate optimization ansatz or algorithm, QAOA, or the variational quantum eigensolver, VQE. And a hand-wavy way of explaining this kind of algorithms is that through discrete quantum operators, they try to follow the pathway given by the adiabatic quantum computation. So each one of these discrete steps are generated through these quantum operators. How good are these methods? On the quantum annealing side, there are already devices with up to 5,000 qubits or units that can represent each binary variable. Then you can set these optimization problems up to 5,000 variables and compare that against methods that don't rely on quantum computing. Here are some results from friends at Los Alamos, where in the x-axis you can see the runtime, on the logarithmic axis, and on the y-axis the optimality gap, trying to solve one of these problems. And you can notice that there are several of these continuous lines that represent classical heuristics, and these dotted lines are mixed integer solver Ruby applied to a quadratic or a linear version of the model. If you zoom into this part, the green line represents the quantum annealer, and you can notice how it achieves an optimality gap in orders of magnitude less amount of time. Obviously, from an optimization point of view, you can say that this is a heuristic method and that it's limited by size and connectivity, but still it shows the potential of this kind of technology. On the other hand, for the gate-based computers, particularly for QAOA, as any approximation algorithm, you can provide an approximation ratio. In particular, QAOA was shown to have better approximation ratios for some kinds of combinatorial optimization problems compared to the best classical algorithms to the date of the publishing of that algorithm. So trying this algorithm is way more limited nowadays because gate-based computers are not of that size. Up until this point, 55 qubits or so 55 binary variables, but that still means that there is a lot of potential, this time coming from a theoretical perspective. Before overselling this, let me tell you about the state of the art. There are only few limited quantum speedup demos, achieved mostly by quantum annealing. And in these cases are in both applications and tailored instances as the one that I was showing in the previous slide. There is not such a thing as quantum advantage yet. There is not an application that we say that it is undoubtedly better to use a quantum computer than any classical alternative. There are, though, two quantum supremacy demos out there by the people at Google and the people in our research laboratory in China, where a computational task was solved on what I would like to call self-simulation. Basically, this task has to do more with the description of the state that represents the quantum computer itself. Simulating quantum mechanics is extremely hard in the classical setting. Therefore, they could achieve speedups of orders of magnitude compared to the best classical alternatives. Having said this, I would claim that there is a world quest on discovering interesting and useful applications for quantum advantage, right? And it's not only me, the one that believes so, but last year, there was over $22 billion invested worldwide in quantum computing applied to what we care about. And I'm sorry if I need to get into some complexity theory. How can we use it for our own purpose? So before that, I would like to show you bounded probabilistic polynomial algorithms, which are basically algorithms that can run on classical computers in polynomial time, at most can fail 1/3 of the time. There is another complexity class, which is BQP. It's the quantum analog of BPP. And in order to observe exponential quantum advantage, a problem needs to belong to BQP and not to BPP. That's precisely the case for integer factorization. And the suspected relationship between these complexity classes is the one that I'm showing in the slides. You can notice that NP-complete and NP-hard problems don't belong in there, meaning that for mixed integer programming, although they lie at this very interesting intersection of interesting from an academic standpoint, useful from a practical point of view, and challenging from a computational point of view, we cannot expect to observe exponential speedup using quantum computers unless P equals NP and the whole complexity classes collapse. We, as a community, as an MINLP community, we are solving on a regular basis these NP hard problems. So this shouldn't discourage us from trying to improve the existing methods in order to get some gains in this. So I would say, welcome to quantum integer programming. I have worked on MINLP during my PhD, and more recently, I have started working on quantum optimization, the relationship of combinatorial optimization and quantum computing. The first project I did was together with the NASA Quantum Artificial Intelligence Lab, where we were writing a compiler for one of these devices, the quantum annealer, using combinatorial optimization. Now, in collaboration with some friends at the University of Lehigh, we started asking ourselves, how would you write down certain optimization problems for them to fit better in the existing quantum computers and take the most advantage of the existing quantum algorithms? That's precisely what we did for the stable set problem and the max K coloring subgraph problem. More recently, together with some colleagues at IBM and ExxonMobil, we started looking into how to model routing problems, reformulate them as QUBOs, and then try to address them efficiently on these quantum computers. As I'm showing you here, if you wanted to compare, let's say, classical methods, mostly branch and bound, or decomposition-based methods for combinatorial optimization against quantum methods, you would see that there is a clear difference between both of them. Mainly, the classical methods, they harness advantages in polyhedral theory with global optimality guarantees, very efficient codes available, but a worst case exponential complexity that might motivate looking into other kinds of methods. On the quantum side, we have methods based on least energy, principal variational algorithms, exploiting quantum mechanics phenomena. But these, to date, are limited by the hardware, and they only have local convergence guarantee. But they could even achieve speedups with respect to the classical alternatives. In terms of unconventional computing, what if you wanted to avoid quantum computing? There are many other alternatives in order to try to build specialized hardware to solve challenging computational tasks. In particular, for solving Ising and QUBO problems, we have already seen some advances using GPUs, using tensor processing units, digital implementation of the annealers, light-based computing, and all of this is based on the QUBO formulation of the problems. So taking a step back, how can we modify our problems in order for them to look like QUBOs? If you have continuous variables, you can discretize them. That's obviously an approximation of the problem, but that's what we need to deal with at this point. And after this, I will only mention exact reformulations. So if you have integer variables, you can binarize them. If you have nonlinear equations in terms of binary variables, they can always be reduced to quadratics by introducing new variables. And the constraints can be penalized and moved up to the objective. Certainly, these, although possible, they might not be very amenable, particularly with the existing quantum hardware that has limited size, given that most of them induce into a problem size growth. And the dualization of constraints is always a challenging thing because you're softening them. What I would like to motivate you to think about is that we have gathered a lot of knowledge on how to decompose mixed-integer nonlinear programming. Why don't we try to apply this in order that we can solve certain subproblems that look like QUBOs, that still get part of the nonlinearity as quadratics and still has the combinatorial structure within it, and apply decomposition algorithms to them. This is not a new idea. People at Los Alamos, D-Wave developers have a hybrid solver, Lagrangian decomposition methods, ADMM methods have been proposed to this end. I would like to highlight something called the test set computation, which was developed at CMU. I showed the left part of this plot earlier, where we have the branch and bound methods and these classical methods. And I would like to show now other kind of classical methods that might have not been as popular as branch and bound methods, which are the algebraic geometry methods. These methods are based on test sets, and its algorithms are based on augmentation, basically where you have an initial solution, and instead of relying on the continuous relaxation of your discrete problem, you are going to hop on the integer lattice in order to find the optimal solution. These techniques use tools from algebraic geometry, and they also have these global convergence guarantees for a subclass of MINLP. There are very few implementations out there, with a big shout out to 4TI2, which are, in my opinion, the best out there, but there are not many alternatives. And interestingly enough, it has this polynomial oracle complexity once you have to test it. I would like to solve a problem, and I'm given an initial feasible solution, an oracle to compare the objective function, and a test set, which is a set of directions. With convex objective, this test set is going to point us from any feasible solution to others that improve the objective function. And if there is one solution where none of these directions point towards an improvement, then we can guarantee that that's the global optimal solution. In this example over here, we see that we have these three directions for this equality constraint AX equals B. If we project this into the X1, X2 plane, you would see that every single feasible solution is one of these points. Let me show you how we can solve using this algorithm the given problem. Now, the test set only depends on the constraints, and it can be computed for equality constraints with integer variables. So for example, assume this convex objective, you want to be as close to the center of these concentric circles. And we start from this point. So using these directions, you would take 3 steps up here until you cannot improve the objective any longer. And then from here, you take a step all the way till this point. Since none of these directions are pointing towards an improvement of the objective function, you can guarantee that that is the global optimal solution for this convex object. I can tell you that the number of steps that need to be taken grow polynomially with respect to the size of the input. Since I started this talk saying that MINLP are MP, or belong to the MP complexity class, where is the MP in this algorithm? And it's in obtaining the test set. And that's precisely what we wanted to tackle by finding this test set through a QUBO reformulation and then using quantum computing for this in the Graver Augmentation Multistart Algorithm. Let me summarize it. We find several feasible solutions classically or through quantum methods. Through quantum methods is just you have AX equals B, quote unquote, you do AX minus B squared, and that's going to be your QUBO, and whichever solution has an objective of 0 is going to be a feasible solution. And this can be adapted depending on the precision. Then calculating the Graver basis is done on a hybrid algorithm on quantum classical. And the augmentation steps are done classically. Given that these only have guarantees for convex objective functions, in order to deal with non-convex problems and partial Graver bases, which we might be interested in finding, we use a multiseed or a multistart version in order to get convergence, right? And this ends up being GAMA. How to find the Graver bases? You need to find the lattice of the kernel. And for this, you need a QUBO. The kernel is the X that satisfies AX equals 0. And this can be easily written down as a QUBO. And then you filter through the conformal minimal elements by comparing using classical methods. Now, once you have done that, you can compute a Graver basis. And this Graver basis is going to give you the test set that you require for the augmentation. And certainly because of precision of these devices, you need to use some tricks on recentering in order to get better results out of the limited existing hardware. An example on capital budgeting, which is a convex MINLP, which might be challenging for solvers depending on the parameters that are chosen here. This we solve with our method, and you're more than welcome to go into the collab repository that is on the slide in order to check out the implementation. We were able to solve this with this method, and just from getting feasible solutions with a single call to the quantum annealer, we can get more than almost 800 feasible solutions. And if we use the complete Graver basis, all these points are going to reach the global optimal solution in more or less 20 to 35 steps. This requires 2 calls to the quantum annealer. This might be too expensive. So with a single call, we can only get a partial Graver basis, but that is enough for almost 10% of the feasible solutions to reach the global optimal. We compared the performance of Gurobi 8.0, which is not the latest version anymore, in order to solve these instances. And we saw how the scaling of these problems end up eventually overpassing the capacities of Gurobi. And on the side of the quantum annealer, we made a series of recommendations of what can be improved in order to get this work better for our own purposes. So if we could increase the coupler precision of the device, if the chip architecture includes not only more qubits, but more connections between them, which is the case for the latest chip. And we estimated how much could we improve. New chips are out there, newer versions of Gurobi are out there. So we are in the process of updating these numbers. In order to wrap up this presentation, I would like to give you some take-home message, which is once we started looking at these problems, we noticed that if the constraint matrix has a spatial structure, you don't even need 4TI2 or a quantum computer or anything to compute those Graver bases. You can actually compute them analytically and fairly fast. This spatial structure shows up in several well-known problems, such as Quadratic Assignment Problem, Quadratic Semi-Assignment Problem, Cardinality constrained quadratic programs. And when we implemented this fully classical version of the algorithm, we were able to observe 100x speedups with respect to Gurobi in instances that we were considering here. We're in the process of rerunning these experiments, getting a paper out of this, but it's extremely interesting that just motivated by these quantum methods, we found this fully classical method with very interesting performance. So, and the applications of this, they cover machine learning, applications in chemistry, in communications, and in portfolio selection. What I think can be done in the future is get better at solving these great nonlinear optimization problems, this MINLP. My opinion is that one needs to use the right tool for the right task. And through decomposition, you can break down your problem into pieces where highly specialized means are there to address the problem. That's, for example, the case of unconventional computing with QUBO subproblems. Why do I care? Well, I'm really interested into energy systems applications, and the better models, the more complicated they are to solve. Therefore, it motivates what in my opinion, we should be spending our time on. Let me conclude here by acknowledging my colleagues at NASA, ExxonMobil, Amazon Web Services, IIT Madras, Lehigh, saying that MINLP is fantastic, right? It's such a powerful modeling paradigm. Decomposition techniques, they have already shown to be very, very useful. So we can try to adapt them in order to use either physics-based or physics-inspired methods for potential improvements. And finally, this is a very summarized version of a course that we designed and taught at CMU on quantum integer programming. We have made the slides, the recordings, the lecture notes fully available online. It has already been replicated in other universities around the globe. So if you're interested in this, I encourage you to please visit this website, and I'm looking forward to the discussion that comes out of this. Thank you.